Okay, so with that, we're going to get into some concurrency. Now, I do have some code I want to show, but before I show code, I want to talk a little bit about what concurrency actually is. I think there's a little bit of confusion that a lot of people have with concurrency. Specifically, a lot of people, when I hear people talk about concurrency, well, here, let me open it up. When you guys hear concurrency, can someone just yell out like 2 or 3 words? What do you think? What's concurrency? I/O. Cool. Anything else? Anyone else have any ideas? More than one thing at a time. Event loops. Yes. Yes. Threads. Perfect. Cool. Okay. So those are all definitely things that are related to concurrency. Threads is an interesting one because it is related to concurrency, but it's also very closely related to parallelism. So you might think that's a little weird. Isn't that the same thing? Parallelism. That's things happening at the same time, isn't it? Right? Concurrency is things happening at the same time. That's true, but there's a little bit more to it for concurrency. Concurrency, very specifically, is related to events that are able to be happening independently of each other. Parallelism is as well, but parallelism literally means they are actually happening at the same time. You have several threads that are all doing work at the same time. When you're doing something concurrently, you don't necessarily have that. You don't necessarily have multiple threads. You don't necessarily have multiple chains of execution happening at the exact same time. An example I like to think about is, let's see, there's probably 20 people in the room. Suppose I were to hand out a deck of cards to everyone in the room, and I asked you to shuffle the deck of cards. We all kind of know that you guys can probably shuffle a deck of cards in 20 seconds or so. So in about 20 seconds, we would have 20 shuffled decks of cards, right? That is parallelism. We have parallelized that process. Now, suppose I went around the room and I collected all 20 cards, all 20 decks of cards, and I brought them up to the front of the room, and I handed one to Michael, I handed one to Fisher, I handed one to Carolina, and I said, I want you guys to take these decks of cards, all 20 of them, and I want you to sort them, sort every deck of cards. That would be happening concurrently. Specifically, the way that Michael is sorting cards is completely irrelevant to the way that Fisher is doing it, which is also completely irrelevant to the way that Carolina is doing it. So she might be grabbing cards off the bottom, Michael might be grabbing cards off the top, Fisher might be starting in the middle, and they don't have to even finish sorting their deck. You can start halfway through a deck, or start with a deck, get halfway done, switch to another one, sort that one a little bit. But the point is that they are all happening independently of each other. So when Michael finishes, Fisher finishes, Carolina finishes, they're all done. So that is concurrency. Does anyone have any questions on concurrency? Okay. Another example I would like to give real quick for concurrency is you can think about like a web server serving pages to customers. If you have multiple CPUs, you can have one CPU to each customer, right? If you've only got one CPU, that has to still serve multiple customers. But it kind of does that thing where it's shuffling the decks and then it's swapping around. So it'll serve a little bit of stuff to one customer, then it'll serve a little bit to the next, then it'll serve a little bit to the third, and then it comes back to the first, and it might go to the third, and then they're all happening independently. That's the important thing. Okay, cool. Let's get into some code. Go is really, really good at concurrency. It's kind of its flagship feature. So let me just make sure this is ready here. Let's get this a little bit smaller. There's a lot of comments here. I'm going to kind of glaze over them a little bit. Yeah, we're going to talk about this code. So the way that Go does concurrency is with this Go keyword. So just take a look at this function real quick, this code real quick. We have 2 functions that exist here: synchronous and asynchronous. Synchronous, we can see that this guy, it just prints a message saying that it's going to sleep for 5 seconds, and then it sleeps for 5 seconds, and then it says it's done. And then we also have, get this off the screen. Also, that one. Okay. Asynchronous, on the other hand, this is, if you've never seen this in Go, this is a really neat little structure. This is a forever loop. It's a forever loop. It never stops. It just runs and runs and runs, which is why this code down here is not unreachable. So yeah, obviously, this prints a message, it sleeps, and then it prints a message, and then it sleeps, and it's going to do that until the end of time, or until I put the program. So now let's look at how this stuff works in main. In main, we have 3 function calls. One, which is here. I'm going to get to this in a second. We have a call to func.println. Func.println is a blocking call. That means that we will run the code that lives in println, and we will not do anything until it is done printing. Once it's done, it will come back up, and we will call synchronous. This is also a blocking call. That means that we are going to sit here on line 19 until synchronous is done. And as we know, that's going to take about 5 seconds. Asynchronous is not going to be blocking. It's not going to be blocking because we have this little go keyword here, which basically says, go do your thing somewhere else. It might be on a separate CPU, on a separate thread, and it might not be. We don't really care, though, because all that we care about is the fact that these are happening independently of each other. That's something I really want to stress with concurrency. Concurrency is a design pattern. It can be used to make things faster, but it really is a how do you think about how code should work. So we're going to go ahead and run this code now. Let's switch over here and run that. It's in Goroutines /main. There it is. And sure enough, you see that we have our first func.println up here. Let me let that run. Sorry. There we go. That's our first func.println. Function is blocking. Synchronous. We can see that synchronous actually printed first. There's some really strange thing here that you should notice. We called asynchronous first. This is the first thing that we did. And yet, when we go into our output, we can see that the first 2 things that were printed are this function is blocking and synchronous. There's a good reason for that. It has to do with the way that the Go runtime handles spinning up Go routines. But again, these are independent events. We don't. Yes. Asynchronous is the first thing we do. We call it with the Go keyword. So, yep. So again, these are happening independently because we don't necessarily need one to happen before the other as long as they all finish at the same time. And so sure enough, we can see we slipped for 1 second 5 times, and then synchronous finished, and the program exited. And it's a good thing that the program exited because technically we are leaking a Go routine here. Like I said, that was a forever loop. It's going to run forever. The Go runtime and our operating system are going to prevent that from hogging a bunch of resources. But it is really important when you're writing concurrent code that you make sure this doesn't happen in your long-running servers. What's up? Yes, so underneath it's doing a bunch of things related to threading and all that kind of stuff. And I would love to go into that talk, but quite frankly, I'm not actually prepared to talk about that right now. So yeah, definitely talk to me after the talk. Yeah, that's being handled for us. That's kind of the nice thing about Go is that we don't have to think about that stuff. We just say, go do this thing, and it does it. It's really, really nice. Yeah, so just real quick on leaking Go routines. If you've got like a web server or I always think because I'm a Kubernetes programmer, a Kubernetes operator that's a long-term running program, you really need to make sure that you are cleaning up after yourself. You don't want these things running forever because they will be eating your resources, and that's no good. Okay, let's see what's next. We're going to go to WaitGroups. So before I move on, anyone have any questions on Go routines or the Go keyword? If I wanted to kill the asynchronous one, well, unfortunately, I don't think there's really a good way to do that. The only way for me to do that would be to break or to return. Cool. So let's see, WaitGroups. So this is not tech. I know this talk says something along the lines of Go primitives. This is not really a primitive. This is a resource that is provided to us in the sync package. WaitGroups are a resource that you can use, and they work. I'm going to use a word that you may be familiar with. It works very similarly to semaphores. If you're not familiar with semaphores, don't worry about it too much. It's a little confusing. but they're quite similar to Synchronous in the sense that these things kind of keep track of how many resources are. Well, let's put it in the Go way. These just keep track of how many Go routines are running. So here you can see I've created a pointer to a wait group. And the first thing that we're going to do with that is we're going to add 1 to it. So this wait group is now waiting on 1 Go routine. Okay, and then this chunk here, let's talk about this real quick. This is a little bit of a weird thing if you haven't ever seen it before. The guy that is starting with func, this is what's called a lambda, or an anonymous function. You've probably seen them in other languages, but basically we're able to spin up functions like this in Go on the fly. By putting these little parentheses at the end, I'm saying call it. In JavaScript, you might be familiar with your immediately executed functions. I think they're called ifs. IFE, yeah, something like that. Yeah, so this is basically an IFE in Go. And then the last thing, of course, is that we are running this. Asynchronously. We are running this concurrently. So we are not going to wait for it to finish. It's going to run in the background. And then let's look at what it's doing. It's going to sleep for 1 second, and it's going to tell us when it wakes up. And then finally, it's going to mark the Go routine as done. So it's going to tell the wait group, hey, I finished, I'm done. You don't need to wait on me anymore. And then finally, down here, we're going to have a print message just telling us that we're waiting. And this call is a blocking call. It will block until all of the Go routines that it is waiting on are done. So I'm going to actually, real quick, I'm going to comment this stuff out just to make this a little bit clear before I get too deep into this. Let's go ahead and run that. And let's see, it just prints a message. Yeah, so just some printing. So that one was wait groups. And there we go. Sure enough. We waited 1 second. You can see there was a delay. I'm going to run it again. 1 second. So Go routine finished. Cool. All right. That all makes sense, right? We're just waiting on the Go routine, and then when it's done, we proceed. Cool. Okay, uncomment with all of that. So, of course, the next thing that we would have to do is consider waiting on multiple Go routines. So in this case, I have a for loop, which is going to iterate 10 times. This is a fun little new for range loop. If you haven't seen this yet, that's how you write a for loop in Go as of 122. And yeah, we're just going to tell it every iteration, wait for another Go routine. Then we're going to spin up this slightly more complicated version of a function, of a Go routine. This one takes the index of the loop as an argument. It generates a random duration, 0 to 5 seconds. It kind of tells us what it's doing, how long it's going to sleep, what its name is, and then it sleeps for that long. And then it's going to tell us when it's done, when it's woken up, and finally it's going to mark that wait group is done. So let's go ahead and run this now. And actually, even before I do that, let me drop back into here. I want to hide this stuff. It doesn't need to be here anymore. Put that out. Make sure this works now. Run it again. Cool. Awesome. So you can see now, the first thing we did was we said we are waiting for the Go routines to finish. Again, even though that these guys immediately tell us that they're going to be sleeping, the order doesn't really matter. We just know that we are going to wait for all of them to finish. And of course, these things all happened very, very quickly. I'll go ahead and run it again real quick so you can see that. That gets spat out instantly, right? Because that is all instant. There's nothing blocking those calls. The important thing here is that these functions were woken up after their randomized sleep time. So looking at each one of these, we can actually take a look. So let's see. Where is our fastest one? It's probably here. It's probably here, 6. And sure enough, it's our first one done. 3 is our next one to finish. So sure enough, they finished in the order that you would expect them to. So that is Go routines. That kind of gets to Kevin's question about how to set them. There's a little bit more involved with your question, obviously. But that is wait groups. Does anyone have any questions on wait groups? What's up? Yes, if there is an error in the lambda, It kind of depends on what kind of error happens. In Go, error handling, as some of you may know, is a little different. Errors are values in Go. But there is a concept of a panic, which is like an index out of bounds. If that happens, that Go routine will crash. It'll panic. But it's only that one that'll panic. And yes, you're right. It will absolutely ruin us because then we'll hit line 55, and that one will never finish. So, of course, it's really important that you're paying attention to your panics, the things that are, things like divide by zero, that the computer just can't figure out. Error handling is done a different way. I will kind of discuss that a little bit. I'm not going to really relate it to errors, but we'll get to channels in a minute, and that's how errors are handled. So we are not really taking any control away. The Go scheduler is really, really smart. So this laptop, I believe it has, I was using had 2 CPUs. This one I think has 32. So when I spin this up, the scheduler in the background, it's going to put each one of these Go routines onto its own CPU, on its own thread. So these actually are happening in parallel. So we actually do get that parallelism here. And these are actually going to happen as fast as possible, as fast as the computer can run. So now, if I were to say, let's do 100 of these, let's run that. Now it's not going to do that. Now these things actually need to they need to coordinate a little bit. We still expect this whole program to last about 5 seconds because, again, these computers are really fast. They can do that swapping up. This is the case where we have 3 decks of cards. Sorry, we have 20 decks of cards and we have 3 people sorting them. So does that kind of clear that up? Yeah. Awesome, cool. Yeah, good question. Yep. When the wait group, okay, so when I say it leaks and there's resources that are still existing, that's because the Go routine still exists, so it still needs compute so that it can still do its execution. So it's still eating CPU time. So there is no literal resource. It's not like in a memory sense that something's being eaten up there. It's still got its stack. There's still a few things that are in there that are being used. But really, the important thing is that the scheduler is going to keep putting that thing back on a thread. It's going to keep running, and it's going to keep using it compute time. So if the function, if the function finishes, it just finishes and it goes away. It just gets garbage collected. Well, if the function finished, it wouldn't be rescheduled. If the function finishes, it's just like any other function finishing. So, yeah. That's a good question. I thought I saw one other hand. Did I? Maybe not. Kevin. Is there? Yep, good question. So the question is there like a finally something to, basically like a try catch kind of thing? Yeah. So if you panic, you can catch that with recover, and then you can actually analyze the error that caused the panic. So that is a thing that you can do. It is very, very. It's basically a try catch block and a fake disguise that you got from the Dollar Tree. People don't like to use it because it's not really how we do error handling in Go. But error handling is its own discussion. I would love to have a talk on that as well. Yeah, good question. And up. Yes, that is a very good question. Let's do that. So what she asked was, can you defer something? Go has this really cool keyword. It's this thing that I haven't seen in any other languages. It's the idea of deferring something. So what that means is that I can do defer. Let's just use Copilot. Sure, thank you. What that does is it says, take this function call and do it when we leave the function. And it doesn't care when we leave the function. So I could say if, let's do if 5, I'm just going to make this if ran number, whatever, ran number, case, whatever, random case, then return. It doesn't matter if it hits this return or if it returns naturally at the bottom of the function. This is going to happen. And that also gets handled with panic. So I'm actually really glad you asked that because I would have totally forgotten about that. Yes, if this were to panic, defer would still be called. So that would actually fix that issue that we talked about earlier that Kevin brought up. So yeah, that's a really good shout out. Okay. Let's see. one other thing I want to mention, just while I'm on this example, you can see that I am always adding one. That's kind of just a best practice to always put a wait group .add one right before you sort of a go routine. There's nothing stopping me from doing this. Put in a 100 here. The problem is that if I do this, now we've got a problem. If I do this, now I've got a different problem. So, one way to do this, obviously, like x equals 10, then you can put that in here. But it's just a little bit easier, a bit nicer for us to just add one all the time. It's a little bit easier to think about as programmers, and that's really the hardest part of programming, is just thinking about things. So, do all of that here, back here. Cool. Leave that. I like this part. That looks, yes. Okay. Cool. Any other questions on wait groups? All right. Cool. Let's talk about channels. So, channels are how Goroutines talk to each other, or how we do communication. Let me open this up. Channel, spelling. Was there a question? Yes, there are other synchronization primitives. Go does have mutexes built in. There's a sync.mutex, and you can use it. I'm about to get into that a little bit here. That's actually really good. That's actually a really good segue, because Go has this thing where we say that you do not want to communicate by sharing memory. You want to share memory by communicating. And that's a super confusing message. It doesn't really make any sense without a lot of explanation. So let's talk about it. In your normal concurrency models, you think about this concept of a mutex. Mutex is, for those who aren't, it's like a key. It's kind of like like you've got a locked room and you've got some resources inside of it, and the mutex is kind of your key to get in. So an example I like to give is, I think this is really easy to understand. Suppose I got a box of Legos, and I want to make those Legos such that only one person can play with them at a time. I might take those Legos, put them in a room, put a key on a hook on the outside, and if I want to play with the Legos, I gotta grab the key, unlock the room, walk into the room, lock the door behind me, do my thing with the Legos. Maybe I'm building a race car, whatever. And then when I'm done, I unlock the room, I step outside, I relock the room, and I put the key back on the hook, and I walk away. Now someone else can come along, they can grab the hook, they can grab the lock, the key, you got it. They can grab the key, they go in, they can build their pony out of Legos, and of course everyone is happy. But there's some problems with this model. There's a bunch of problems. So for example, what if I get to the room and the key's not there? What if someone has taken the key with them and they never put it back? I took the key and I brought it to Home Depot and I made a copy of it. Now I've got two keys. Someone's in the room playing with the Legos, and I walk in on them, and now I'm going to take their Legos and I'm going to build my race car, regardless of how far along they are on their pony. Yeah, so there's a couple of problems with mutexes, and obviously, as programmers, we are trained to work around those things, but it is a little bit painful to think about that. So the way that Go does this is it uses this concept of channels. Channels are kind of like a mailbox, kind of. And basically, the way that this works is that instead of putting the Legos in a locked room, I have the Legos in a box. I just take them out of the box and I play with them. And when I'm done with the box, I say, okay, here, it's your turn. You get to play with the Legos. Now you are playing with the Legos. And as long as you have the box, you get to play with the Legos. There's no like locking mechanism that's associated there. It's just a matter of you literally have ownership of them. So it's yours now. You can do whatever you want with it. And I don't have ownership. I don't even know it exists anymore. So that's kind of a high level on what channels are and how they work compared to mutexes. I know it's probably a little confusing. Everyone kind of with me on at least the ideas there. All right, cool. I'm going to show some code. Yes, it is. Mutex is basically just, it's a semaphore with a value of 1. Goroutines kind of avoid all of that. So Goroutines, they have a little bit of a strange syntax, so kind of bear with me here. When we create a channel, Yeah, channel type weird syntax. When you create a channel, you have to use this make keyword. And when you create the channel, a channel is a channel of something. In other words, you have to put something into the channel. And that can really be any structure, any resource that you can create in Go. So in this case, this is a channel of integers. But there was nothing stopping me from making this a channel of strings or a channel of foods or whatever. Those will all work. So in this case, we're just using integers just because it's a little easier to understand. This code is going to be using a prefix on everything so that we can kind of see which Go routine is talking. We're going to have the main Go routine. We're also going to have the Go routine. Sorry if that's a little confusing. So what we can see here is that we're creating that channel. And the first thing we're going to do is we're going to call the function send. We're going to do that concurrently. We're going to hand it the channel. And I'm actually going to, let's see, I think it's this stuff down here I want to comment out. And then let's go talk about how send works. So send takes a channel. Let's zoom out just a little bit. Perfect. So again, here's that syntax for channels. In this case, I've actually specified that this is a send channel. You can only send on this channel. You can't receive from it. You can only put things into it. So it's kind of like, it's if you're the mailman, you can put this into the mailbox, but you can't take it out of the other side of the mailbox. So what this function does is it prints a message telling us that it is going to send a value into the channel. It's going to put something into the channel, and then it's going to sleep, and then it's going to do some other stuff that I'm going to actually close out for now. So not sure what that was, but all right. Okay, I think I've got the right amount of code commented out here. So what this is going to do is we're going to see this message get printed, or maybe this message get printed, and then we are going to see this message get printed, or again, some other order of those things. And then there's going to be this thing that's called that I call the synchronization event. The thing about channels, the thing about unbuffered channels, and we'll get to buffered channels in a second, is that if you put something in the channel, you can't do anything until someone else has taken the thing out of the channel. In other words, this line, 35, is a blocking call, unless there's something in the channel. If there's something in the channel, we grab it and we just keep moving. In the same vein, this is also a blocking call. We are going to sit here, because we have put something in the channel. We cannot proceed until someone on the other side has removed it. There's an image that I want to show real quick that kind of demonstrates this. This is kind of that concept. This is that concept of the mailbox. You can see in this case that the guy on the left is putting the baton into the channel, and he's stuck here on frames 2 and 3, and then on panel 4, this is that synchronization event. The right guy pulled it out, and now we're able to proceed. So basically, what that means for us is that we know that line 48 and line 35, we're going to finish those two things at the exact same time. So let's go ahead and run this code. I'm not exactly sure what this is going to look like. So bear with me. Channels, and here we go. Starting Go routine to send. Yeah, so means it's sending. Now it's waiting. Go routine spins up. It says that it is sending a value. It sends it, and then it is received on the other end. Okay. Does that make sense? The synchronization event, the way that this kind of stuff is happening. What's up? Yes. So I don't think I can do it here. I don't think that it functionally makes. Maybe I can. I can do it. That's very interesting. I actually don't know what the value of this would ever be, because
that's how I wasn't 100% sure.
Yeah, that's very interesting. I had no idea. That's a good call out. Okay.
But yeah, so you just take a general channel and you make it send one.
Yes. Yeah, precisely. So this one is a read-write channel, but whenever I send it, whenever I give that channel over to the send method, send function, It is now a receive only. In other words, if I did, let's see, if I did x equals receive a value from the channel, and then I would turn on my diagnostics. Whoa, undo. No. Yes, turn on diagnostics again. Yeah, you can see that's an invalid operation. You cannot receive from a send only channel. We kind of saw that the second of the same thing with the send. Cool. Yeah, good call out. Yeah, that's so this is Vim, so it's not an ID, but yeah, it's that is Go PLS running in the background, which is the language server protocol. If you don't know what language server protocol is, you should really look into it. They're awesome. They're super cool. You're probably using one, you don't even know it. Yes, it runs basically automatically in VS Code. So no, it would not have if I put this back, and I put this up here, and then I switch over here, and I say go run, we're going to see that exact same error. Cool. Yep, good question. Okay. Let's see. I'm going to move a little quickly here. I was planning on being done here by 6:45. Oh no, I got 20 minutes. Good. Okay. So let's. Yes. Oh, another question. What's up? Sorry. Can you just say it again? There's nothing. Wrap. Oh yes. So you're saying I do something like this. Go from, and then do this. Yes. This also works. It just wait. This. This makes it non-blocking. Now that kind of misses the point, because that synchronization event is the important thing. That's why we do it this way. That's why it works this way. We actually want those things to be synchronized. There's other ways around this, and I'm gonna get to that in a minute. How we can kind of avoid this synchronization event. No one likes when we do that. So, yep. Yes. Yep. Yeah. I mean, that's basically we're passing that data around. It was kind of like I was saying with the idea of a mutex, is that once this 42 is sent over to main has the 42. No one can change it. If it was a variable, if it was a structure, if it was something else, it is now owned by main. And so main kind of knows, oh, it's my turn. It's my turn to use the 42. It's my turn to build a race car with the 42. I know it doesn't make sense, but yes, precisely. And there is some interesting considerations for that. For example, if I pass a pointer to a struct across a channel, there's still a pointer in the calling function. So you do need to be careful when you're thinking about things like that. If I'm passing the whole struct by value, that's great. If I pass a pointer to the value, well, now there's multiple pointers, or rather, the pointer is still owned by whoever has it. But you get the point. You know, there's still. Yes. Yep. Yes. Exactly. Yes. As long as yeah, that's exactly correct. Cool. All right. Let's this last one in this function, this snippet. So now we're going to do something a little more complicated. We're going to send a lot of things on the channel. If we look at send. We're going to be sending 10 items now into the channel. So kind of the same thing as with the wait group. We have this for loop that's going to iterate 10 times. It's going to print a message saying that it is sending a value. We're actually sending the integer across now. And then we don't need the wait here. The wait kind of makes the output a little more understandable. But again, like I said, like we've seen several times, message output I/O gets a little strange sometimes. So I'm literally putting the sleeps here just to make it very clear. But yeah, so let's go ahead and run this and see how this. Oh, let me actually explain it first. So again, there's going to be a synchronization event. It's going to happen now on line 55. The other end of that is up here. So Go has 4 range loops. They work exactly the same way as every other language. We've kind of already seen that example down here on line 52. That's a for range loop. But you can also range over a channel. And what that means, when you range over a channel, is read values from that channel until the channel is closed. And I haven't really talked about closing channels yet, but that's the thing you can do. So you can close a channel. It kind of says, I am never going to send anything into this channel ever again. It's done. We don't need it anymore. There's no way to reopen it. It's a completely, it's a dead object now. Yeah, it's kind of like putting the cap on the channel. So that is exactly how this is going to work. This is going to iterate until the channel is closed. So let's see, make sure everything is in here. We see that we are sending the value, we're printing, and then once this for loop finishes, once this for loop finishes, we are going to have one more sleep just to, again, to keep the I/O clean, and then we're going to close the channel. And that means that the send function will have finished. It will return. It will be done. And so once it's done, we will, the program's going to exit. So let's take a look and see what happens. So I'm going to clear the screen real quick. That is those channels. So there's our first one. Here we go. And again, synchronization event. That's the important thing. These are happening at the exact same time. I'm going to go ahead and throw some spaces in there so you can really see the separation between how these things are working. What's important to notice is that, and I actually do want to show this because I was talking about this before the other day. If I remove this sleep and run this, now we see some weirdness. These things get flipped. Looks like main is going twice, and then the go routine is going twice. But really what's happening is that these two things happen. Sorry. This one and this one are happening. This is happening in the background. So it's happened after that has been sent. This I/O just happened to come afterwards. So the synchronization event still happened, but then the I/O just took a second to get it out. So just a little bit of an interesting thing that we noticed the other day. And again, just keep it safe and makes it really clean. So cool. Does that make sense to everyone? I know channels are a little confusing. Everyone on the right page? All right, I got 12 minutes. I'm going to hit buffered channels. So I showed this image earlier. We also have this concept of hang on, it's in the tab. There we go, an unbuffered channel. So this is kind of the same thing as a channel, except that now there's we can say there's some space. There's some space for things in the channel. It's more like instead of having a mailbox that has space for one thing, you've got like a tunnel that you're pushing things through. And the really important thing about buffered channels is that they are not blocking. They do not block. So what that means is that you can see in this example, the guy on the left is putting things in, and he's doing some more work over here as well. In panel 2, you can see that he's got his hand in there, but he's also over here grabbing another baton so he can put it into the channel on pane 3. And in the same way, this guy, I don't think you can see because the image gets cut off, but yeah, he's reaching in and he's grabbing the baton out, and he's also reaching the channel. So these are not blocking calls. And what I want to show here, I have a small example of the buffered channel. So in this case, here's our buffered channel. Again, we have to use that make keyword. Make optionally takes a second argument. In this case, I've said the buffered channel is going to have a capacity of 3. We want 3 slots for integers in this channel. And then we're going to fill it. I use an older period address because I wanted to get the 1, 2, 3. So again, this is unblocking. This is not blocking. So we put the item, we put the 1 in, we print the message, we put the 2 in, we print the message, we put the 3 in, we print the message, and then we proceed. And yeah, this is kind of trying to give a mental model of what that channel will look like. You've got kind of an output here on the left side, an input on the right side, and you've got these values in there. If I didn't have all the values in here, there would be just spaces in here where you would have space available for those things. In our case, it's filled. So now we're going to spin up a go routine, and in that go routine, we are going to put a for on the channel. That will block. There is no space for it. So this one has to wait until something has come along and taken in this case, the 1 out of the channel. channel. Once it's number one, we'll have this case, this thing, another space, so the 4 config. And yeah, so this is finally it is going to close the channel because again I want to have this nice little folder down here on line 33. I do make a point here to sleep because I want to show that this is definitely a blocking call. And let's go ahead and take a look at run that. It's buffer channels go. There we go. Sleep to make a point, and then once everything once it's finished sleeping, it starts reading from the channel. We know that there is a 4 kind of just sitting here hanging out on line 23, but the instant that the 1 gets ripped out on line 33, the 4 gets put in, and this line 34, this happens very, very quickly because it just very quickly drains that channel. It empties it out. So the reading out happens very fast. Okay. Any questions on buffered channels? Cool. Let's see. I have one more thing I want to show. This is the select statement. So this one. Okay, this is a terrible program. Do not write code like this. What this does is it creates we call it a slice in Go, but you can think of it as an array. It's just a list of integers. We've got a list of integers, and this actually creates 2 separate channels. One which I'm calling oddch, and the other one is called evench. And then we're going to spin up 2 separate functions, odds and evens. They're going to take the oddch and the evench channel. We're also going to take that full list of integers. It's going to see all 10 of them. And then let's just take a look real quick at what these are doing. They're pretty straightforward. These are kind of like, if you're familiar with generators in Python, they're a little bit like generators. They are asynchronous, so there's no yield like there is in Python. But basically what these are going to do is, in the case of the odds, it's going to iterate over all 10 integers. It's going to look and see, is that number odd? And if it is, we're going to put it in the channel. And once we've done that, then we're going to sleep for some very brief period of time. I just wanted that because it makes it a little bit clear what's happening. Same case for the evens. It's even we put it in the channel that we received. Notice that we call these C here in both cases. That might be a little confusing, but the point is that they're going into the channels here that are that are corresponding to them. Okay, select. Let's take a look at select. Select is a keyword in Go that allows you to sort of pivot on channels. It basically says, I'm going to wait until there's a value in a channel, one of the channels that I have a case for. And as soon as that happens, I'll execute that block of code. So for our example, we have the even channel and the odd channel. Whichever one gets done first, whichever one has a shorter sleep time, or random sleep, that's what's going to happen. We're going to see those being picked out. And then, yeah, so what's this? Run it. I think that's good. That was select. Go. And there we go. Sure. 1, 2, 3, 5, 4, 7, 9, 6, 8, 10. We got every number kind of happened in a random order. And that makes sense because we were randomizing the timing. And every time I run this, it's going to be a little bit different. We kind of expect that 1's going to come early and 10's going to come late, but they're always going to be a little bit randomized. And they will always be kind of just happening as they are readily available. So, does that make sense to everyone to select? The ability to kind of watch multiple channels and say, okay, which one is ready? As soon as one's ready, I'm going to pull that out. Yes, that is a good point. Okay, so that's another thing. Yes. So there is a switch. Yes, there is a switch in Go, and it works the way you would expect, except for what Scott just said. In Go, you do have to specify that you need to fall through. So that looks like this. And I think you can no, you cannot do that with select statements. You cannot do that with select statements, and that kind of makes sense because you wouldn't have the num here. You would have been able to read from the channel. But yeah, so in Go, you can use switch statements. They don't need breaks. I know you're saying it sounds nice, and it really kind of is when you're writing it, but it's a little weird because every other language does it differently. So Anyway, that's for another time. The last thing I want to show with select is that, much like a switch case, it has the opportunity to have a default case. So let's just get that formatted real quick. So what that means is that this for loop is running. It's going to run until we have received all the values. That was the reason I had this num receive thing. There's nothing stopping you from doing it forever. And in fact, you'll see that happen a lot. People will do this a lot. So actually, just to really make the point clear, let's do this. Do this. Actually, you know what? This is not a good idea. This is not a good idea. Let's fix it. I'm just gonna prove the point. This closes the channel when it's done. This closes the channel when it's done. And I suppose this is actually worth discussing. I didn't plan for this, but this is important. When you close from a channel, select will no longer try to read from it. So when we run this now, we'll see the same thing. Except, maybe not. I've got something wrong. Let's see. Do some live debugging real quick. Select 4 because I have 4 here. Because now we got to the end. So there would be a way to fix this. Yeah, I'm not going to spend too much time on that. But yes, the point is that, here, let's do it this way. Let's make it clear. Let's do pump.sleep, pump.print, receive a value. I don't know what this is. I'm just going to delete it. And then we're going to go into time.sleep. Let's just do like 100 milliseconds. All right, cool. Some live coding. Make sure this works. No, it doesn't work. Oh, well, sorry. No, that does prove what I'm trying to say, though. This is going to happen every time. It's going to keep running, but we're not going to try to read from these channels anymore. So, just check this. Okay. Don't worry about that. I'll need to look a little bit closer at this later. All right. So the default case, this will happen every time if there is nothing in one of the channels. So again, main is up here. It's sitting here. It's waiting. It's looking at the even ch and the odd ch, and it's saying, as soon as there's a value in one of these, I'm going to grab it. I'm going to do something with it. But every now and then, it's going to look into those boxes again, and there's not going to be anything in either box. So if that's the case, we're going to see this happening. So let's run this, and hopefully I didn't break everything. No value to wait. There we go. Yeah, so it's going to do that every time. It's going to get there very quickly. And I have no break statement, so we do see this exploding at the end. Oh, right. This is it. Can I do reset? Yes. Cool. So just to show that final working code. Yeah, there we go. It works nicely. Cool. That is default. That is select. And I have 1 minute to spare, which is awesome. I did not expect to be that close. Does anyone have? Oh, it's no longer true. It's no longer true. Yes, this will actually block. So let's go ahead and prove it. Put that there. Put that there. This is going to close the channels. I don't want to close the channels. I'm trying to figure it out. And not only will I not print anything, but I also won't increment number seeds. So this should just hang. What am I doing wrong? Printing that it's odd. Did I not comment out? Sorry. Are you talking about? Well, yeah, but I'm only incrementing num received when I actually receive a value from the channel, and I'm never receiving value from the channel. So, yes, there we go. Now they're all blocked, and now we've created a deadlock. So yeah, it was blocking, and that's what we're talking about with the deadlock. Of course, if I wanted to run like a server, I would have it. It would sit there and it would stop and it would wait until someone came and requested a page from my web server. So yeah, that's really kind of the normal use case for select statements. You'll also see people use there is a context package which has things like timeouts and tickers and that kind of stuff, so that you can actually do other things that are like I just used the default and then used the time.sleep, but there are resources built in that allow you to say, okay, I want to do something every 5 seconds, but if I get like a message, I want to do something different, or I want to sit here and wait for something to happen. But if 5 minutes passes, I want to stop waiting. So I'll listen on the timeout channel instead. And as soon as I receive a signal from the timeout channel, I'll stop. So yes, that's a really good question. Yes, it would. So that's kind of exactly, that's really the point. Yeah, I actually don't know if I see select. I don't know if I see default used very often. But again, I kind of hinted at the tickers and the timeouts. Those are the things you really see more often than going to the default. But yeah, well, good questions. Yes, that's what we're showing here. That's what happened in this execution, is that we never received on the channel, so we created a deadlock here because the for loop is now blocked, waiting for something to be sent on it, and nothing ever got sent. Yes, there are a couple things we can do. There are, as far as I'm aware, without digging into something like the unsafe package, which there might be in the unsafe package, I don't know of any way to necessarily influence which Go routine it is going to pick. I think that is more or less handled for us. We do have things that allow us to run the garbage collector at will, so that might have an impact on that, depending on what your code looks like. We also have this thing. Let's see if I go up here. I can do runtime dot. Which one is it? It was go max procs. Go max procs. I think I can. This is more of I thought this was a function. There's a function in the runtime package that allows you to specify how many CPUs to actually use. So by default, it will just use all of them. But if I wanted to limit it to only use two CPUs, I could do that. And again, asynchronous concurrency. If we don't necessarily need to worry about how these channels are working, we just know that they are working, and more processes just makes it faster. But the independent events is really what's important. I don't know if I really answered your question. I hope I at least helped. Michael.
You don't have to answer it too much, but if you select.
Yes, that's another thing I should have mentioned very early on. Yes. So when you receive from a channel, this is actually really important. When you receive from a channel, you do this thing called comma OK. This exists for a lot of things in Go. It also works for maps. Like if you try to key into a map, the OK is a Boolean, and it says, in this case, the channel is open, or the channel is closed. So, yeah, I could absolutely. Let's see how quickly we can figure this out. Well, if I'm trying to read from it and it's closed, it will do nothing. It'll skip over it. Yes. If I try to send something to it and it's closed, that is a panic. Yes. Yeah. Cool. This. I don't think I can do this. I can't do that. I don't think so. Yeah. It's definitely. I guess I might do something like if okay, and then handle it in here. Yeah, that's how I would do it if I really wanted to debug into it. Yeah, but as we've seen, the live code is not really. I'm kind of that's not one up. All right. Yeah. Same. You mean like for a buffered channel? Yes. So that is in. Let's switch it back over to buffered channels. So when we create buffered channels, we do specifically buffer them by using the second optional argument to make. So I could delete this, and now it's no longer buffered. And of course, I could also. This is important. I can do this. That's one spot, but it is still buffered, which means that it still will have non-blocking calls. And in fact, just to make it, oh no, this won't work because this is going to block now. Yeah, this will die. But yeah, that's That's how you would specify the value. And in fact, I see people do this a lot of the time. I kind of mentioned that you can change the number of values. Change the number of CPUs. If you call that function with the number 0, I think it returns how many CPUs you actually have. So you'll see people do that where they do runtime. Maybe it'll help you? Yes, something like that. There we go. Now it will use exactly as many. Now, now I know for sure that these are all going to be happening at exactly the same time. They're all going to be running in separate parallel. Cool. Recommended buffer size? Yeah, it kind of just depends on what you want to do. Again, it comes down to. Sorry. Yeah, so it really is again concurrency. So like when you think about parallelism, the whole point of parallelism is our program is slow. We have to make it faster. Concurrency, again, it's a design pattern. So if you want to spin up 1,000 Goroutines, there's nothing stopping you from spinning up 1,000 Goroutines. Unless you have 1,000 CPUs, they're not all going to run in parallel. But it just depends on your use case, I think. So it's a design pattern. What's up? Yes, yeah, because exactly. As we kind of saw in like the first couple of examples where like the I/O is all sorts of messed up. That's because of the Go runtime. It has to schedule these things onto the actual threads in the computer. So if you have a ton of Go routines, now the scheduler is working really, really hard. This was a fun thing that I did back when I first started learning about Go routines. Was I tried writing an asynchronous version of quicksort. As we hopefully all know, quicksort can be written asynchronously because basically you're just saying sort the left side, sort the right side, and then segment those down from that. So there's really nothing stopping you from saying send off 2 Go routines to sort those 2 things. That works. It works out to be slower than just not using Go routines. It's really weird. Yeah, again, when it comes to that kind of thing, it's a lot of the time you just need to benchmark. It's kind of the same thing as everything else. So, yeah, Larry. Oh. I don't know exactly what it is that's slowing it. It's really, I would assume it's because so Go routines are basically like micro threads. They aren't literally threads, and they get scheduled to threads. So each thread manages one Go routine at a time, and then when that Go routine goes to sleep, the Go routine is taken off the thread. A new Go routine is put on the thread. And it spins up like that. That is the part that takes time. Is taking those things off, putting them off into the run queue, letting them run back to the run queue, and then loading back into the thread. So I think that would be why it's slow. I honestly don't know for sure. It's in the guts of Go, in the guts of the scheduler. But yeah. Any other questions? All right. Awesome, guys. I think that's it for me today. All right. Like I said, I'm going to leave this up on the screen. We do have the room until 8:30, so if you want to hang out and talk, feel free to do so. I would love to talk about Go. I thought we talked about
So yeah, and just for the benefit of those still hanging out online, be sure to like, subscribe, and smash that notification bell. So, all right, everybody, thank you.
Cool. Thanks, Paul. Thanks, everyone. Thanks, everyone on the live stream.